For the first talk this afternoon, we're going to have Bowen Wang from Pagoda, who's going to be talking about the evolution of near protocol design. So coming to you from San Francisco, please welcome Bowen.
Hey, how's everyone doing? Good. Cool. As we'll introduce, I'm Bowen from Pagoda, and today I want to talk about the evolution of the near protocol in the past several years and where we're heading towards next. It'd be ideal if this works. Okay. So as you probably all have heard of, we started with Nightshade. And this is the white paper that we published in 2019. And it details a design for a completely sharded blockchain. So both transaction processing and state are fully sharded, which at the time was not something that people take for granted. And one of the key innovations of Nightshade is that it only maintains one chain. Each shard does not maintain its own separate shard chain. And this allows us to get around some of the very difficult problems, like the atomistic failure of cross-chain transactions. And another key feature of Nightshade is that execution is entirely asynchronous. No matter whether two contracts live on the same shard or they live on different shards, if you want to do a cross-contract call between those two contracts, the execution is always going to be asynchronous. And the security of Nightshade relies on fraud proofs. So the assumption is that there is at least one node fisherman tracking every single shard, so that even if an entire shard is corrupted, meaning that it's controlled by malicious validators, it is possible for the system to recover because fishermen can submit a fraud proof so that once the fraud proof is verified, the state would roll back. So despite all the innovations and simplifications in design, Nightshade is still a very complex protocol to implement. So Alex and I came up with this four-phase approach to actually get to Nightshade. In phase 0, we launched mainnet with one shard, even though all the code is written for many different shards. And in phase 1, which we launched last year, we introduced chunk-only producers, which adds some sharded processing to the network. And according to the roadmap, the next stage would be full Nightshade, essentially implements what the original white paper envisioned. And it is a system where no validator would have to track all shards, so the entire system is fully sharded. And after that, the plan was to have this enhancement where the system would dynamically adjust based on the load. It would change, increase number of shards when there's more load, and it would decrease number of shards when there's less load on the network. So in the past several years of developing and evolving the roadmap, what we realized is that Nightshade is a very elegant design, but in practice there's a big problem, which is fraud proofs. So not only fraud proofs are quite difficult to implement, because essentially you need to have a way to statelessly verify that the invalid state transition has happened. But also, it is actually quite dramatic change to the network, because when fraud proofs are verified, we not only need to roll back the state of one shard, but actually the state of all shards need to be rolled back simultaneously. This is because otherwise someone can corrupt one shard, means 1 billion tokens sent to another shard, and even if you roll back the state of that shard at the moment, it doesn't solve the problem because the 1 billion tokens that are invalidly minted already live on another shard. So the state of all shards have to be rolled back at the same time, and this can actually happen at any time, right? It can happen when the epoch switch, when the validator set change, when there's resharding, or like when there's congestion on the network, and there's like a lot of corner cases to be accounted for. And what makes things worse is that this mechanism is almost never expected to be triggered in practice, because as far as I'm concerned, there has been no attack in the proof-of-stake world where an invalid state transition has actually happened on the network due to malicious activities. And this makes it very difficult to test that this mechanism works correctly. And the problem is that if this mechanism does not work correctly, it can actually accidentally slash people due to bugs under normal operation, and that is actually quite difficult to deal with. So we ask ourselves the question, is there an alternative? And there is. So that's where stateless validation comes in. So this is a different design where the system has two types of validator. There is stateless validators who essentially receive the chunks and also the state witness that are required to be able to verify the execution of those chunks. And there is a separate set of validators called chunk proposers. Essentially, they're responsible for producing the chunks, keeping track of the state locally, produce state witness, and distribute them to the rest of the network. So the obvious question is like, well, how does this help? So basically, there are two important things with stateless validation. One is that when you sample a subset of validators for a single shard from the entire validator set, if there are a lot of validators, the probability of a shard getting corrupted can be made extremely small. And the probability a shard getting corrupted, meaning that it's controlled by majority of malicious validators. And also, the validators will actually shuffled on every single block, so essentially the rotation happens on every single block. And because of that, there is no way to adaptively corrupt the validators for a given shard because you don't actually know who are the validators who are going to validate for the next block because the shuffling actually relies on the randomness beacon that you cannot bias. And as a result, the system is probabilistically secure and with extremely high probability. So roughly in practice, it means something like on the order of once every 1,000 years or once every 2,000 years, the validator rotation will fail. And so in practice, that can be considered secure. And this allows us to essentially get rid of the fraud proofs. That is the most difficult thing to implement in the Nightshade design. But that's not the only major benefit. There are actually at least two other major benefits of the stateless validation design. So one of them is that the cost of operating a validator is going to go down significantly because they don't actually need to track the state of shard locally. And as a result, they can operate much cheaper hardware. And because of that, it potentially leads to more decentralization and more validators joining the system. Another thing is that because only a few validators in the system need to operate more expensive hardware, we can actually make it such that the state of a shard can be entirely held in memory, and this would improve the speed, the performance of single shard dramatically, because today we know that performance bottleneck is mostly on state read and write. And those validators don't even need to operate super expensive hardware either. This is because we're sharding, so we can essentially say that the state of each single shard is limited to, say, 50 gigabytes. And if you do that, then ideally it should be able to fit into a 64 gigabyte RAM machine, which isn't really that expensive either. So the team has already begun working on this new design a few months ago. And we expect the engineering work to finish by the end of this year and actually release to mainnet in Q1 2024. So it is worth highlighting that this design, or like what we're implementing now, actually completes the phase 2 of sharding goal, where no validators need to track all shards. Despite it being a different design, it does achieve what the vision of the Nightshade paper says. And we plan to have more optimizations in the future, things like reducing the size of state witness, improve network communication, improve the reward structure, and so on and so forth. So in our pursuit of excellence, we never fail to ask ourselves the question of whether we can do better. And in the stateless validation design, there is essentially a different difficult problem, which is that the state witness, it actually consists of the state touched during the execution, alongside with a Merkle proof that the state actually belongs to the correct state as dictated by the state root. And the size of the state witness could be a concern, especially when the network is under high load, so the state touched during the execution could be a lot. And we're asking ourselves the question, well, is there a way we can get around that problem or at least mitigate it? That's where Starsight comes in. And before I talk about what Starsight actually is, I want to take a quick detour and talk about zero-knowledge proofs, one of the hottest topics in blockchain today. I won't actually go into too much detail on how exactly zero-knowledge proof works, and I'll only give a high-level overview of what it can do and what it can enable. So essentially, for an arbitrary computation P, you can generate a zero-knowledge proof to prove that the computation is done correctly, and the proof is succinct, meaning that the verification time is polylogarithmic in the computation itself. And depending on the construction, it can also be constant time, meaning the verification is extremely fast. And also it has input so that the verifier doesn't necessarily need to know the input to the computation. So for this presentation, we'll mostly focus on the part that the succinctness part, meaning that the verification is extremely cheap. And because of those properties, zero-knowledge proof gave rise to a lot of interesting possibilities. They're very small, very cheap to verify, and verification of the proof is highly parallelizable because verification of each proof is stateless. You just verify the proof itself, and you can verify like 10 proofs at the same time. And why is this important? So if we think about what blockchains do, one of the most important things blockchains do is that they reach consensus on what the state is. No matter where the blockchain is started, it's one of its main tasks is to actually agree on the state. And today, most blockchains do that by verifying the computation. So what that means is that, let's say, some node does computation, let's say it produces block, it does a computation, and it gets a new state root, and all the other nodes in the network, assuming, let's say, there's one shard, then all the other nodes in the network needs to redo the same computation to verify that the computation is done correctly. And that is actually a lot of overhead. So let's say you have 100 validators, and essentially there's like 100x computation overhead. And zero-knowledge proof actually breaks away from that kind of paradigm. And it only adds a little bit of overhead because each verification is extremely cheap. So on top of the original computation being done, the overall overhead is quite minimal if we exclude the proof generation time. So what does this proof actually do? So roughly, it states that there exists some chunk whose execution leads to the new state root. And this proof has 3 parts. The first part is that this proof that shows that there exists some chunk that would hash to the given hash. So the given hash is a public input to the zero-knowledge proof. So basically, both prover and the verifier knows about it. And also has a proof that proves that the state used during the execution is correct, meaning that it belongs to the correct state as dictated by some state root. And finally, it has this most complex part that shows the runtime execution is correct. And this essentially is a circuit that encodes entire near runtime logic. So it's not only just things like transaction execution of transfers or like simple things like this, but also includes a smart contract execution. And because Near uses WebAssembly as a runtime, it also proves the WebAssembly execution as part of this proof. And as you probably have heard yesterday, this is the Dekawasam initiative that we're working on with the Polygon team. So despite all the magical properties of zero-knowledge proof, they're not without problems. So one of the biggest problems with zero-knowledge proof today is that proof generation is quite slow. So the most performant decay system today has a slowdown factor of roughly 10,000x, meaning that it takes 10,000x more time to generate the proof compared to the native execution itself. And that number is going down pretty dramatically over the past several years, and we do expect that number to go down dramatically over the next several years as well, due to innovations both on the proving system and on the engineering side. However, there's still a problem. Let's say the overhead gets down to 100x, meaning that the proof generation time is 100x execution time. We still cannot integrate into the protocol as is, and that is because Near is designed to have fast finality, very low block time, and blocks are produced very fast. It's not designed for this system where there is a 100x overhead between consensus and execution. That is what motivated us to design Starsight, a decay-centric sharding model. So roughly what this says is that the consensus would run separately from the execution and only agrees on the transaction to be included in a block. And the people who execute the block, the chunks, let's say we still call them chunk proposers, they would execute the chunks and generate the proof for the state transition. And once the proof generation is complete, the proof would get committed back into the blockchain and get validated through consensus. And those proofs attest to both the new state root as claimed by the chunk proposers, as well as the new outgoing state root, so that there can be cross-shard communication. And with techniques like proof compression or proof recursion, this design can actually scale to quite a large number of shards, even if we just put the proof directly in the block. So in terms of scalability, we think that Starsight is as good as Nightshade. So this is kind of an illustration of what I mean by consensus running separated from execution. So as you can see, this is showing the execution of one shard. It's not necessarily the case that there is a new state root update after every single block. It could be that whoever does the execution execute several blocks together because it's always running behind consensus, so it always has something to execute. And at some point, once it generates the zero-knowledge proof, it will commit the zero-knowledge proof back into the consensus, the blockchain. So there are two major advantages of the Starsight design. One is that the design is extremely simple, except the decay part. So there's no validated rotation, there's no fraud proof or state rollback. That is one of the main difficulty in the Nightshade design. And because the new state root are essentially atomically committed back to the blockchain, meaning that they are either immediately accepted through consensus because all the validators would validate the zero-knowledge proof, or they're immediately rejected as invalid. This simplifies a lot of the design challenges we had in Nightshade or similarly in the stateless validation design. And the design is also very versatile. It doesn't dictate how the chunk proposer should package transactions. They can potentially even be shared across multiple different shards and so on and so forth. And more importantly, it doesn't really dictate how the runtime should actually work for each shard, as long as zero-knowledge proof can be generated for the state transition. And this gave rise to a lot of interesting possibilities. So for example, we can have multiple execution environments within the same network. Potentially, we can have WASM, EVM, Move, or some other custom virtual machines. And it's also possible to conceive a future where we have both synchronous execution and asynchronous execution within the same network. So for example, we can have WASM execution environment similar to what NEAR has today with async execution and EVM with synchronous execution. So this is kind of a comparison between Nightshade and Starsight. And in terms of security, Nightshade relies on system having honest fisherman, and Starsight does not rely on any additional security other than the BFT assumption. They both have very high scalability, and Starsight has much higher decentralization factor because verifying the state transition is extremely cheap, can even do that in the browser. And even though Starsight somewhat sacrifices on-chain finality, as we think in practice, that's not that big of a concern because the RPCs can actually, as long as they have the transactions, they can execute them and provide this kind of optimistic state finality. And for people who want more kind of a security from the chain itself, they can get it when the zero-knowledge proof is committed back to chain. And assuming a 100x slowdown factor is like 1 to 2 minute delay, which in the grand scheme of things is considered to be acceptable. And in terms of execution environment, today the Nightshade design relies on WebAssembly, and in Starsight is pretty much any execution environment that can be proved in ZK. So since the mainnet launch in 2020, we've had 34 protocol upgrades, and we're constantly searching for ways to improve the protocol, exploring different frontiers of the blockchain research, and try to improve the usability, scalability, and decentralization of the NEAR protocol. And Starsight is just one of those efforts to explore the next stage of evolution for the NEAR protocol. And we are working on a white paper that documents the details of the Starsight design. I hope to publish that somewhere in early 2024, so stay tuned for that. And that's it. Thanks.